This video is for AQA Physics Combined Science Higher Paper 1. I've taken my other whole topic video and reorganised it for this year's exams based on the advanced information. If you are not doing physics, then go and look in the description down below and it will take you to the other videos. So the Edexcel videos when they're ready, the paper 2 videos, the biology videos, the chemistry videos. But this is for AQA Physics Combined Science Higher Paper 1. Very specific video. We're going to go through things that are the major focus, we're going to go through the practicals, we're going to go through the other stuff that's not listed but is going to come up in low key marks, and it does not include the stuff that is not on the exam. To go with this, there is the workbook which has been moved around and redigged and resorted out for this year's exams over on my website, and the predicted papers which will be out at the beginning of April. The law of conservation of energy tells us that energy cannot be created or destroyed. It is only transformed into another type of energy, which is really cool because it tells us that the energy you're going to have for lunch or breakfast today has been around since the start of the universe. That the energy that's powering your computer, your phone, your lights has been around since the start of the universe. And the energy that you are using, the kinetic energy, the chemical energy that you are using today to get out of bed, to do your daily things, is going to be around till the end of the universe. Kinetic energy is equal to half times mass times velocity squared. Kinetic energy is measured in joules, half is just a number, mass is measured in kilograms, and velocity is meters per second. And with this, remember, it's just the velocity that's squared, not the whole thing. Elastic potential energy is equal to half times the spring constant times extension squared. Elastic potential energy is measured in joules, half is just a number, extension is measured in meters, and the spring constant is measured in newtons per meter. Gravitational potential energy is equal to mass times gravity times height. Gravitational potential energy is measured in joules, mass is measured in kilograms, gravitational field strength is 9.8 newtons per kilogram, and height is measured in meters. Change in thermal energy is equal to mass times specific heat capacity times change in temperature. Change in energy is measured in joules, mass is measured in kilograms, specific heat capacity is measured in joules per kilogram space degrees C, and change in temperature is measured in degrees C. Power equals energy transferred over time. The units for power are watts with a capital W, energy transferred is joules with a capital J, and time is seconds with a small s. Power is equal to work done over time. Power is measured in watts, work done is measured in joules, time is measured in seconds. Power is equal to potential difference times current. Power is measured in watts, that is a capital W, potential difference is measured in V, and current is measured in amps. Power is equal to the current squared times the resistance. Power is measured in watts, capital W, current is measured in amps, and resistance is measured in ohms. Energy is equal to power times time. Energy is measured in joules, that is capital J, power is measured in watts with a capital W, and time, seconds with a lowercase s. Energy is equal to charge times potential difference. Energy is measured in joules, charge is measured in coulombs, and potential difference is measured in volts. The national grid is how we get electricity from power stations to our houses. Yeah, power stations generate the electricity and they move it to a step-up transformer, and then through a network of cables and pylons this gets moved across the country to a step-down transformer and then into our houses. Step-up and step-down transformers are an important part of our national grid. They work by having a varying number of coils on each side depending whether it's step-up or step-down down transformer. A step up transformer will turn a low voltage into a high voltage so that the energy can move through a system, electricity can move through a system with less energy loss, making it more efficient. Whereas a step down transformer will take it from a high voltage into a low voltage so it's safe to be in our homes. Solid particles are in a fixed position. They do vibrate, but very, very slightly, and it is around a fixed position. They do not move around. Liquid particles move around much more. They're still touching each other, but they are not in a fixed position. They are moving about randomly. It's still rather limited movement. It's still within a confined space. Unlike gas, which is free to move and zip around all over the place. If we're going to be putting energy in, then we are going to be turning a solid into a liquid, or we are going to be evaporating a liquid into a gas. If energy is coming out of the system, a gas is going to be condensing or a liquid is going to be freezing. Density is the amount of mass in a set volume. So mass in a set volume. And this is the same for the equation. And the equation for this is rho. I know it looks like a lowercase p, but it's not. It's a lowercase rho equals mass over volume. The units you need to know for this: mass is measured in kilograms, volume is measured in meters cubed, and density is measured in kilograms per meters cubed. In this video, I'm using a simulation from the excellent PhET website. You can see here we have a closed container and I'm adding in gas here, and we can see the pressure. As more gas goes in, we can see the pressure is increasing. So it's stabilised. I'm going to add in lots more gas here, and you can see the pressure is going to increase. So as the gas bumps against the walls of the container, it's exerting a small force, it's doing work on there, and is going to be increasing the pressure in the system. An atom is incredibly tiny. The word atom means uncuttable, and it's so tiny that the Greeks who named it an atom thought it was the smallest thing, but it isn't the smallest thing. We know there are things inside of it. Now, I said it was incredibly tiny. Its size is 0.1 to 0.5 nanometers, which is 1 times 10 to the minus 10 to 5 times 10 to the minus 10 meters. Now, inside our atom, we have protons and neutrons, and in the shells on the outside, we have electrons. This bit in the middle here, this is called a nucleus. Protons and neutrons are located in the nucleus, whereas electrons are in the outer shells. Protons have a mass of 1, neutrons have a mass of 1, and electrons are incredibly tiny. Their mass is 1/2000th that of mass of a proton or a neutron. Protons have a charge of +1, neutrons have no overall charge, and electrons have a charge of -1. On the periodic table, you will see two numbers. The larger number of the two is the mass number. The smaller number of the two is the atomic number. It does not matter where these are located. Different books, exam boards are going to put these in different locations. It does not matter where these are located. The mass number is equal to the number of protons plus the number of neutrons. The atomic number is equal to the number of protons and also equal to the number of electrons in an atom. So if you want to find the number of protons, that is equal to the atomic number, whereas if you want to find the number of neutrons, that is equal to the mass number minus the atomic number. Here we have boron. The mass number is 11. The atomic number is 5. So if you want to find the number of neutrons, that is mass minus atomic. 11 minus 5 gives us 6. Protons equal 5. Electrons equal 5. Now, protons have a positive charge, 1, 2, 3, 4, 5. Electrons have a negative charge, 1, 2, 3, 4, 5. So an atom, and this is for an atom only, will have the same number of positive charges and negative charges, which means there is going to be no overall charge in an atom. An ion is going to have lost or gained electrons. So for example, if we have take our boron again, with our 1, 2, 3, 4, 5 positive and 1, 2, 3, 4, 5 negative charges, if it loses an electron, it now no longer has the same number of positive and negative charges, so it's going to be charged. It has created an ion. Here we have two isotopes of carbon. You can see they have the same atomic number 6 but different mass numbers, which means each of them is going to have 6 protons. They're each going to have 6 electrons, but when it comes to the mass number, one of them has 12 minus 6, 6 neutrons, and one of them has 14 minus 6, 8 neutrons. Isotope is an atom that has a different number of neutrons. The model of the atom has changed a lot over time, and it's changed because we have new developments and new discoveries. From ancient Greece, where they developed the word atom, uncuttable, to Dalton, where it was a solid sphere, J.J. Thomson, who discovered the electrons, where we had a plum pudding model, a positive sphere with negative bits dotted through it, Rutherford, who did the plum pudding experiment and worked out that it had a solid centre, Bohr, who developed the nuclear model of the atom. Now, I know the writing's very small on here, that's because you don't need to know the exact details, you just need to know the overall developments. Rutherford gave us the positive centre, which we call the nucleus. Chadwick added in neutrons, and then Bohr developed this nuclear model that we use today, with a positive centre and electrons orbiting outside. Rutherford wanted to test the plum pudding model, which was a large positive blob with negative bits dotted throughout it. So he took a sheet of gold foil and a gun that fired out particles, and he shot them at the sheet of gold foil. Now, the majority of these particles went straight through, but very occasionally one would get deflected a little bit, and even more occasionally one would get deflected a lot. And this told Rutherford that instead of it being an evenly distributed pattern of negative and positive charges, we are likely to have an overall build-up of positive in the middle, with negative charges around the outside, so that the majority of the atom was made up of empty space, and this led to the development of the nuclear model of the atom. There are 3 types of radiation: alpha radiation, beta radiation, and gamma radiation. Alpha radiation is also known as a helium nuclei, beta radiation is also known as an electron, and gamma radiation is part of the electromagnetic spectrum, it's a wave. A helium nuclei and alpha radiation can be rewritten as alpha for 2, mass of 4, positive charge of 2. An electron can be written as E, mass of 0, charge of -1, and gamma is again just a wave. Alpha radiation is very large, whereas gamma radiation is very small. Alpha radiation is highly ionising, whereas gamma radiation is not. Ionising means how good it is at knocking electrons off, so how good it is at turning something into an ion. Gamma radiation is highly penetrating, whereas alpha is not. To stop alpha radiation, a bit of paper or a bit of skin will do it. Aluminium foil or thin foil will stop beta radiation, but thick lead is needed to stop gamma radiation. A Geiger millitube will measure radiation. It generally clicks every time it hears a bit of radiation, and the unit for radiation is the becquerel. A half-life is the time it takes for half the radioactive atoms to decay into something else. We can use that as a graph. If we take 100% and 50%, read across with a ruler and down, 50%, cross with a ruler and down, and that there, the time between having 100% activity and 50% activity, or whatever value, and half of whatever that value is going to be the half-life. The half-life of something can range between very quick milliseconds to thousands, hundreds of years. The calculations for this are a lot simpler than they look. Here we have uranium-238. It is going to go alpha to K. Alpha is 42. So we have 238 minus 4 gives us 234. 92 minus 2 gives us 90. Then we need to use the periodic table to look up what has an atomic number of 90, giving us thorium. For beta decay, we have minus beta, 0 minus 1. 238 minus 0 gives us 238. 92 minus 1 gives us 93, which gives us neptunium. It does not matter about the mass number for these calculations, the atomic number is the important thing. Different isotopes of an element are going to have different half-lives. Back in the lab again. Here is our setup for specific heat capacity. We have our blocks. We have our thermometer. We've got aluminium set up at the moment. And we have iron and copper. We can take our start reading on the block, and in the hole in here we need some water. We can see this is connected up to a power unit, so we're going to have the power going in through here, and we have this connected up to a multimeter, but you might have it connected to a voltmeter, an ammeter, or even a joule meter. Here we have a diagram of the practical. We have our block, our thermometer, and you need a tiny bit of water in here just to get rid of this air gap, so that the energy in here can be transferred easily and read by the thermometer. This is our heating element and it's going to be connected up to power. What it's actually connected up to will vary depending on what equipment your school has access to. It can be connected up to a joule meter where you can read the joules directly, or like I've used, it can be connected up to a voltmeter and an ammeter where you have to do a tiny bit of maths. So here is my complete circuit. You saw in the video I was using 12 volts for my power input. The actual reading on the multimeter was 9.8 volts and then the ammeter reading was 2.8. I've drawn the circuit here kind of like correctly, not including a multimeter, so we have our ammeter in series and our voltmeter in parallel across the component that we're measuring the potential difference across. It is highly unlikely that your measured voltage across the component will be the same as what your power pack is set to. There are 3 current potential difference graphs you're expected to recognise and draw. Remember, current here is measured in amps and potential difference is measured in volts. A resistor at a constant temperature, the current and potential difference are directly proportional to each other. For a filament bulb, we have our graph going through 0 looking like this. This is because as the temperature increases, the resistance increases. And a diode will only let current flow in one direction, so the graph looks like this, the direction that it is pointing. While energy cannot be created or destroyed, it can be wasted. Wasted energy is any energy that comes out of a situation that we didn't intend for it to be there. For example, in a light bulb, we have electrical energy going in. This is converted into light, heat, and sound. The light is the useful energy, whereas the heat and the sound are not useful energy, they are wasted energy. And a word the exam would love to describe this, we can say that the wasted energy dissipates into the surroundings. It spreads out so much it can't be collected and used. It's not gone, it's still there, it's just spread out, it's dissipated. Heat comes off and we can detect that with an infrared camera. We can see how well the house is insulated. The blue parts, the roof, are very, very cold, so not much heat is escaping. Whereas the walls here and here are very, very hot, so lots of heat is escaping. We can see that the roof is blue and the windows are blue, suggesting they're very good insulation. New houses are built to be very energy efficient and old houses can be adapted to be very energy efficient. So we can have cavity wall insulation, double glazing, loft insulation, carpets, curtains, draft excluders. If they still have them, they could have a jacket around the hot water tank. Efficiency is equal to useful energy out over total energy in, and this can be expressed as a percentage or decimal. Efficiency is equal to useful power out over total power in, and this can be a percentage or a decimal. When we're thinking about generating electricity, we can either do that with a renewable source or with a finite source. A renewable source is one that isn't going to run out. We can get more of it, whereas a finite source is going to run out. Renewable sources include things like the sun, the wind, water including tidal power, hydroelectric power, wave power, geothermal power, whereas a finite resource is going to be a fossil fuel, so coal, oil, gas, or nuclear power. The advantage of solar power, the advantage of the majority of renewable resources, is that they don't release carbon dioxide. We're never going to run out of them, and they're generally non-polluting. The disadvantage of solar is that it doesn't happen during night and isn't very good on cloudy days or wintry days. It can also be expensive to install. Wind turbines, a disadvantage of wind turbines is that some people don't like them. They also don't work very well on non-windy days. Tidal and wave power can be disruptive to the local environment, whereas a hydroelectric dam involves flooding a large area which may include people's homes or animals' habitats. And the disadvantage of geothermal power is that it can only be used in volcanic countries. The advantage of using fossil fuels or nuclear power is that they are very, very readily available. It's a very, very cheap source of electricity, and things like coal power stations have a very short startup time. The disadvantage of using coal, oil and gas is that they take millions and millions of years to create, so we are about to run out of them. They are very, very heavily polluting, so they release large amounts of carbon dioxide and other pollutants into the atmosphere, which contribute to climate change. The disadvantage of nuclear power is that you have to store the nuclear radioactive waste for long periods of time, and there is a very small, but there is a potential risk of explosion. You need to know all of these circuit symbols. I've made you handy flashcards for this, but here is a quick recap. This is a cell. This is a battery. You will notice that a battery is more than one cell put together. Here we have an ammeter, voltmeter, a lamp or a bulb, diode, an LED, light emitting diode, resistor, variable resistor, fuse, thermistor, LDR, light dependent resistor, closed switch, open switch. Charge is the value of electricity flowing through a circuit. Current is the flow of electrons. Potential difference is what pushes the current around, and resistance is anything that slows down the current. Charge equals current times time. Charge is measured in coulombs. Current is measured in amps. Time is measured in seconds. Potential difference equals current times resistance. Potential difference is measured in volts. Current is measured in amps. Resistance is measured in ohms. A thermistor is used in stuff like your central heating, and it's only going to let current flow at certain temperatures. For example, at a high temperature, our graph looks like this, whereas at our low temperature, the graph is going to look much lower. So as the temperature changes, the resistance changes. For a light-dependent resistor, whether the lights are on or off is going to depend on the quantity of light. We can use this in street lights or security lighting. If we have a bright light, that's what our graph is going to look like. But then if the light dims, it is going to change. So the resistance flowing through the circuit changes with the amount of light. Ouch! This is why in some videos I have unexplained scratches.